Welcome back to the deep dive. Today, we are opening up a file that dropped right around Christmas 2025 and really shook the foundation of modern web infrastructure.
It really did.
If you work anywhere near React or Next.js, this is your wake-up call. We are diving deep into the analysis of a critical remote code execution flaw. It's known as React2Shell.
That's CVE 2025-55182. And this vulnerability, it isn't just a simple misconfiguration. It's a design flaw. It targets the fundamental communication mechanism of modern server-side rendering.
And the headline finding is it's staggering.
It is. The core finding is that this exploit, at least theoretically, allows an attacker to gain full server control, unauthenticated RCE.
With a single HTTP request.
With just one single meticulously crafted HTTP request.
The shock factor here is, it's truly immense. When we say RCE, we're talking about total compromise of the server environment. This is not about stealing a few cookies.
No, not at all. This is about becoming the application's owner.
Full control.
Exactly. And, the sophistication required to chain these logic flaws together is high, but once defined, the attack itself is actually low friction.
So our mission today is to pull apart that underlying architecture.
Right. We need to look at React Server Components as RSC and the proprietary React Flight protocol. And then we follow this highly complex, multi-stage narrative that transforms what should be harmless UI data into
executable Node.js commands.
Precisely.
Okay, let's start there. Let's start with the architectural shift that even created this new attack surface, React Server Components, or RSCs. For our listeners who are familiar with classic React, what's the difference? Why is this so critical?
Well, the fundamental difference is where the code executes.
Yeah.
Traditional React components, they run entirely in the client's browser.
Right, on my machine.
On your machine. RSCs, however, they execute exclusively on the server. That means Node.js, V8, Edge environments. It's a massive paradigm shift.
Because it completely changes the trust model.
It fundamentally changes the trust model. And when you say server execution, you're talking about privileged access.
So they're running in the application's inner sanctum.
Absolutely.
Yeah.
RSCs have direct access to resources you would never, ever expose to a browser client. Things like live database connections, file system operations, internal APIs.
And the big one, environment variables and secrets.
Exactly. Your API keys, your database passwords. So if you compromise an RSC, you have, for all intents and purposes, breached the fortress.
Okay, so if the RSC is doing its work on the server, it can't just send JavaScript bundles down to the client anymore.
Correct. That wouldn't make sense. Instead, the RSCs generate a serialized data model.
A serialized data model, so a set of instructions.
That's a great way to put it. It's a set of directives that describes the UI structure, component references, props. It's essentially an internal language.
And the mechanism for speaking that language across the network is the React Flight protocol.
Yes. React Flight is this binary-like transport layer. It's designed for high-efficiency streaming component data in these small incremental chunks.
But here's the kicker.
Here's the critical vulnerability point. This communication, it all happens over exposed HTTP endpoints, usually something like RSC in the Next.js application.
Wait. So you're saying the attacker isn't exploiting the application logic that I wrote using React?
No.
They are exploiting the communication protocol itself.
That is the key distinction. Anyone can send arbitrary flight payloads directly to that endpoint. You can completely bypass all the checks and balances of the client-side React runtime.
And that leads us straight to the core flaw, doesn't it? The complete breakdown in the trust boundary.
It does. It all boils down to a broken trust model. The foundational assumption that the designers made was that these incoming flight payloads, the serialized data, would only ever originate from trusted sources.
Meaning the legitimate React client code that they wrote.
Exactly. So the server was just programmed to accept and rapidly reconstruct whatever data stream it received. No questions asked.
It's like the brain just trusts any signal coming up the spine, assuming it's from the body. And this moment of deserialization, that's the moment of highest risk.
It is. That's a perfect analogy. Deserialization is incredibly complex. It's parsing the payload, it's reconstructing these sophisticated object graphs in memory, resolving module references.
And React2Shell just abuses that trust.
It abuses unsafe deserialization. The attacker injects malicious data that the server blindly trusts and reconstructs, and that allows them to steer the execution flow during the reconstruction phase. The problem is simply insufficient validation of client-controlled data.
I have to say, following the exploit chain that the researchers discovered, it felt like watching a grandmaster play chess. Just so many moves ahead.
It is truly intricate.
Let's take it slow. Step 1. The attacker needs a tool, a gadget, to run arbitrary code.
They need the skeleton key to the JavaScript engine itself. And in this case, that's the highly dangerous function constructor.
The one that evaluates strings as executable code at runtime, every attacker's dream.
It's the ultimate goal.
So how do they find it? How do they get a handle on it? This brings us to prototype traversal.
Right. So prototype traversal is the key here. Every JavaScript object maintains a link to its blueprint via the prototype chain, the proto property.
Okay.
The attacker uses the normal flight chunk referencing syntax, which is just designed for looking up data, to instead climb up that prototype ladder until they reach the global scope where the global functions live.
Can you just walk us through the actual path they take? It's fascinating.
Certainly. So they start with just an arbitrary object reference, let's call it $1. They then append a traversal path to it, proto.constructor.constructor.
So from the object's prototype to its constructor,
Yeah.
and then to that constructor.
Exactly. So they jump from the object's internal prototype, they find its constructor, which is usually object, and then they access the constructor of that, which ultimately resolves to the global function constructor itself.
Incredible. So it started as a benign data lookup, has now given them the power to create and run any code they want.
They now have a weapon. They can call function, shell command. But just having the function isn't enough. You need the vulnerable server code to actually call it for you.
How do they trigger it automatically?
And that's step 2, thenables.
Right.
And the enable is basically any object that has a .then method. It doesn't even have to be a real promise.
Okay, just an object with a method called then?
That's it. And the critical language behavior they exploit here is that if your application code runs await obj on a thenable, the JavaScript runtime automatically invokes that then method.
Oh, I see. So the attacker crafts a malicious object, gives it a then property, and they inject the function constructor they just found into that property.
Right.
Then when the server's own legitimate, uncompromised code simply executes an await on this deserialized object, boom, the attacker's function gets called.
That's the theory. But there's a problem here. At this point, the arguments being passed to function are just internal callback functions. It just results in an error.
So they're close, but they haven't achieved RCE yet. They can't control the input to the function.
Exactly. They need more control over the internal state of the React flight stream itself.
Which is where they break the object boundary in step 3.
Correct. They use this very special React Slate syntax at id.
So if $1 returns the resolved value of a chunk,
Then at $1 returns the raw chunk object itself.
the raw machinery.
Precisely. This bypasses the normal safe resolution process. It exposes internal metadata fields like status, and most crucially, the response object. The attacker is no longer just looking at the data. They are manipulating the internal streaming system.
So they have raw access now. What do they do with it?
Step 4. They force a second deserialization pass. They take their malicious chunk, and they set the client-controlled status field to the string resolved model.
And React's internal logic just trusts that status.
It assumes only its own trusted code would ever set that status.
How?
By supplying it externally using the delet syntax, the attacker forces the system into this very specific, very vulnerable internal state.
I see. And setting resolved model triggers logic that parses the chunk's value as JSON and calls another internal function, revive model.
Which initiates a second deserialization pass.
Why is that second pass so crucial?
Because that second pass, step 5, enables what's called a context confusion attack. The revive model function uses the now fully attacker-controlled response object as its execution context.
The confused deputy.
The classic confused deputy attack. Think of the server as a deputy, dutifully executing commands, but the attacker has just swapped out its instruction manual for a malicious one.
So the attacker controls this malicious response object. What are the key things they hijack?
They hijack 2 things using prototype pollution. First, they redirect a specific internal function, response.formData.get, to point back to the global function constructor they found earlier.
Okay, so one part of the machine is now pointing to their weapon.
And second, they inject their arbitrary RCE payload code, the actual shell command, into another field, response.prefix.
So the weapon and the ammunition are now in place, just waiting for a trigger.
Exactly. And that comes in step 6, the blob resolution trigger. The nested JSON payload in this second pass contains a blob reference, something like $0.
And when React tries to resolve that blob,
The vulnerable internal logic executes the function that's now at response.formData.get, which is function. And it uses the string from response.prefix plus the blob ID as the argument.
so because prefix holds the RCE code, the final result is function, RC code here gets called.
A new executable function is created. And because the whole thing is still wrapped in that thenables, the server's legitimate wait logic immediately executes it. The shell command runs.
That entire 7-step chain,
Oh,
it's astonishingly intricate, taking legitimate JavaScript features and
Right.
weaponizing them through a series of logic flaws.
It's a masterclass in exploiting complex abstraction layers. It just shows that when frameworks evolve this quickly, the security of their internal protocols often lags behind.
So let's pivot. Let's talk about the impact. Why should every single organization running Next.js or React care deeply about this?
Well, first, we're talking about massive global exposure. React and Next.js are everywhere. E-commerce, enterprise apps, government platforms. A successful compromise means total application ownership. An attacker can pivot from your web server into your internal network, your database, your cloud environment.
And this high impact is coupled with low friction. No memory corruption, no authentication needed. It's scriptable.
Highly scriptable, meaning once an exploit is written, it can be deployed at scale by relatively unsophisticated attackers. And you have to consider the failure of traditional defenses here.
Your Wave, your web application firewall.
Right, you might feel safe, but waves are designed to look for common attack signatures. SQL injection, cross-site scripting in predictable formats like HTML or JSON.
But this attack is happening during the parsing of a proprietary binary-like protocol, React Flight. It's happening before any of your application logic even runs.
Exactly. The vulnerability exists entirely within the deserialization process. It's before routing, before authorization, before any of your sanity checks. A way looking for suspicious SQL isn't going to catch a logic flaw buried deep inside a serialization library.
That's the nightmare scenario for security teams. You're flying blind. So for you, the listener, what are the immediate, actionable protection steps? This has to be the priority.
First and foremost, patch immediately. This is the highest priority. You have to upgrade to React 19.2.1 or later, and Next.js 16.0.7 or later.
And crucially, the serialization libraries, too.
Yes, make sure things like React Server DOM Webpack are updated to past versions. If you're running an affected version, you are currently vulnerable. It's that simple.
And given that RCE grants access to memory and environment variables, the second critical step is, it's painful, but vital.
It is. Assume compromise and rotate secrets. This can't be overstated. If you're running a vulnerable server, you have to assume that all critical credentials exposed to that backend were compromised.
API keys, database credentials, cloud tokens, all of it.
All of it. Rotate everything. It's a necessary recovery step.
So beyond patching and rotating secrets, what does proactive hardening look like for this kind of flaw?
Layered defense. The principle of least privilege has to apply rigidly to your RSC servers. Run those environments with minimal OS and cloud privileges.
Use read-only file systems if you can.
Absolutely. An attacker who gets RCE on a Node.js process that has very few permissions can do significantly less damage.
And finally, monitoring. What are the indicators of compromise, the IOCs, that teams should be scanning their logs for right now?
Look for suspicious POST requests that are specifically targeting those RSC endpoints, especially the RSC path. And look for any unexpected shell command execution originating from your Node.js processes.
Things like an id command or wami.
Or attempts to read sensitive files like etc password. Those are major red flags that the RCE chain has been successfully executed.
To synthesize all this, React2Shell is just a perfect demonstration of how these complex, modern architectures like RSC, which deliver incredible performance, also introduce surprising risks when they're built on implicit trust.
I think the key takeaway for everyone listening is that the most sophisticated features often expose the most surprising vulnerabilities. They expand the attack surface into these internal, trusted protocols that developers just assume are safe.
Which brings us to a final provocative thought for you, the learner, to consider as you go check your package versions. If the mere act of converting network data back into an object, the act of deserialization, can be weaponized into unauthenticated RCE, what does true zero-trust deserialization actually look like in practice?
And how do developers vet the internal security of these highly complex, binary-like protocols like React Flight that they didn't even write?
It forces us to ask if the performance gains are always worth the risk of these opaque, proprietary communication protocols.
A very important question.
Food for thought indeed. Thank you for diving deep with us. We'll see you next time.